Okay. Yeah, okay. I can speak. Hello. We're Alex and Giuseppe. We're going to talk about our experiences in building a Kubernetes cluster on bare metal hardware for Wikipedia. So first, some information about what we are. I think most of you are familiar with our main project, which is Wikipedia. The Wikimedia Foundation is the non-project organization that works on maintaining the infrastructure for Wikipedia, but not just Wikipedia, other sister projects like Wikidata or Wikitravel, Wikisource, and so on. Not WikiLeaks, which is... as you can see, we have a healthy amount of traffic monthly. So we are one of the top 10 websites as far as traffic is concerned. Still, we have our infrastructure as two primary data centers where the application layer stays and the persistence layer stays, and then we have 3 caching data centers, one in San Francisco, one in Amsterdam, and a new one in Singapore, that are basically just keeping the caches of the content so that we can serve the content nearer to the user. So it's kind of our own home-baked CDN. Even with the amount of traffic that we have, our cluster is relatively small. We just have 1,200 hardware machines. We don't typically use VMs in production. Just lately, we're using a couple of Ganeti clusters that host about 100 VMs. And we're not just lean in terms of hardware, we're also lean in terms of the size of the organization. As you can see, around 160 engineers overall, and the people that care about the application layer, which is what we're moving to Kubernetes, is just 4 people. So, why we're moving to Kubernetes? Just a few words about this. And up until 2014, we just had the big monolithic application, which is MediaWiki. And one service, which is called Parsoid, that was helping with our visual editor. Fast forward 4 years to today, we have much more services. We are moving somehow towards a microservice-oriented architecture, slowly, but even with this slow motion, the toil on our team, which is very small, is increasing and increasing. And we need a way both for us to work faster and for the developers to be able to deploy their services better and with less weight on our time. But these are not the only reasons to move to Kubernetes. One big reason for us is elasticity. So the ability to scale up and scale down each function that we have in a short amount of time after traffic bursts. And also, well, the fact that it kind of frees up us from having to deal too much with the failure of a physical node, because Kubernetes will basically detect its out and reorganize resources by itself instead of having us doing that. And also containers are a good thing because they allow developers to have basically the same consistent environment on their own development machine and in production. So that reduces surprises when things are coming to production. And finally, we are giving the same developers, the people that deploy the code on the cluster, more control over their applications, because the configurations about resource utilizations is not anymore in Puppet, which is controlled by us. So they can have much more flexibility about what they do. But we also saw some challenges. So the first one, Kubernetes is complex, as we've just seen in the previous talk, right? Just the QoS is very complex and everything else is complex and there are a lot of moving parts. We didn't want to sacrifice the stability that we have just to get flexibility. Also, it's a new paradigm. Anyone has heard cloud native in the last few days? Yeah, it's a new paradigm and it's a good thing, but it's also a problem for all the tooling that we have around our cluster, which is based on the concept of having physical servers with services installed on them. And finally, containers are also a challenge for us because we're used to be very efficient in doing security upgrades, and everybody that has dealt with containers knows that's kind of almost unsolved problem on containers. So, why we're doing things on bare metal? Why are we at the Cloud Native conference talking about installing things on bare metal? Well, there are some reasons why we can't use a public cloud. First and foremost is that we value the privacy of our users very much and the contract that we have with our users in terms of their privacy. And we feel that if we add a third-party actor in the middle, we have to trust that third party fully in order to give the user the same guarantees, and that's not going to happen with public cloud. Also, we already have our infrastructure, we're already maintaining it, so it's not like we have an upscale cost for just maintaining a bare metal cluster. And finally, costs, as I said in the first slide, right? We have quite some traffic, quite some amount of traffic. Think of the bill of just taking all those bytes out of a cloud, what that would be, and we don't really have money being a non-profit and relying on donations of individuals. Why we're not doing a private cloud then? Well, we already do it actually for another project that we run on top of OpenStack with Kubernetes, but that's a platform as a service for editors that can build tools that help them edit the wikis. For the production path, we felt it's not really something we want, because we want to reduce the number of moving parts, right? And OpenStack is actually more moving parts than Kubernetes. So we didn't really see the reason to do that, because the elasticity we need is already given us by Kubernetes itself. Since we want to move all the application layer to Kubernetes, we have a set of machines that are dedicated to that, and we just want to switch resources between one and the other. And so we don't need the additional elasticity that's given by cloud. So this is it for my part, and I'll let Alex talk about how we set up the cluster.
Hello, everyone. Nice to be here. So talking about how our clusters are set up, we have a very Debian developer populated SRE team. There are a lot of those people there, and that's why we decided to go, of course, with the Debian packages way. So we package our own Debian versions of Kubernetes, and very, very recently in this conference we found out that Google is also providing Debs for people, so thank you for that. We aim to evaluate them, and if they are good enough, use them, and I'm hoping that they are, because maintaining that package is a little bit of a pain. Anyone who has ever gone into the process of building Kubernetes can probably attest to that. So we currently are at version 1.7, and which is, of course, as you probably know, unmaintained right now, because Kubernetes team only maintains the last 3 releases. So it's 1.8, 1.9, and 1.10 that are currently maintained. And we need to upgrade, of course. And maybe we'll be here next year telling you how we upgraded to all these versions. We also use Calico. For those of you who do not know, it's a CNI plugin, basically, for Kubernetes. And we are currently at version 2.2.0, and of course 3.0 is out. And again, we need to upgrade. And we are also using etcd 2.2.1, and you're probably already asking why are you not on 3.x? And the answer is yes, we need again to upgrade. We're packaging all this software on our own, and we need to maintain it. Our clusters, well, we're a very big Puppet shop. If you want to go to our Gerrit, or you go to GitHub where we have a mirror of our Gerrit, you can see our Puppet repo. It's, I think, the biggest open source Puppet repo there is out there, even though it doesn't have a license, but don't please judge us on that. So we configure everything via Puppet. So we configured all of the Kubernetes components via Puppet as well. And that had one very nice thing. It allowed us to have TLS for all the components everywhere from the go, just by reusing the Puppet CA. And also showed a couple of problems with the Puppet CA in the process. We would like at some point to solve these or migrate away from it. We will see. What we do not maintain via Puppet, even though we pondered the idea, was the Kubernetes resources. There is even a Puppet module in Puppet Forge that allows you to do that. But on thinking about it, we realized that maintaining such a Puppet module and making generic enough and all that, and publishing it in Puppet Forge would be a pretty big toil. And then we even realized later on it would not make sense for our case, because we end up maintaining most of the resources, if not all of them, via Helm at the end. A little bit more about how those clusters are set up. We have API servers, 2 per cluster. and they are behind a load balancer, an in-house load balancer, which I will describe a little bit more in detail afterwards. And we also have the kube scheduler and the kube controller manager also on the same node, and we pass dash select masters and true equals true. And the reason for that is that it allows us for those two components to be on the same node as the Kube API server and talk to it on the unauthenticated port and just rely on firewalling in order to protect our API. That allowed us to avoid, for now, authentication and authorization that we would need to do for those two components of Kubernetes to talk to the API server. A little bit more about those two production clusters. They are currently 3. Well, one is not really production, it's the staging cluster, which we are now binding to our built-in deployment pipeline. And we have one per primary DC. We were talking about the primary DCs previously. We have separated these TCD clusters for every one of those Kubernetes clusters, and of course we use the basic idea of 3 in order to maintain quorum. They are of course DC local in order to maintain a low level of latency. And funnily enough, those are on VMs, on Ganeti VMs. Ganeti is a mature virtualization orchestration framework by Google. Thank you, Google, for that as well. You can expect what we run kubeproxy in the default way, which is IP tables mode, but we are evaluating IPVS. We're already a very heavy LVS DR shop, and so this is actually interesting for us, and we do have expertise already in this. And we host our own registry, and we enforce it. We do not allow things off of Docker Hub running in our infrastructure. And the reason for that is what you can probably guess, and a lot of people have said in this conference, is that you cannot guarantee, if you're pulling things from Docker Hub, you cannot guarantee what you're running, and most importantly, even if you can trust the person doing it, has he, she updated the specific image that you are running? So what we do is we build and run all our images from scratch, and you can even go around and check out our images. Your Docker pull command is there. Feel free to see what kind of images we have. They're, of course, very specific to our use cases, but feel free. Of course, they are, well, Debian-based. As I said, we're Debian shop. The backend for this specific Docker registry, which uses the reference Docker registry from Docker, is OpenStack Swift, and it works reliably well, remarkably well. We went with RBAC, role-based access control, from day one. And the reason for that is very simply we're not cloud. We cannot have our Kubernetes clusters in the cloud, which means that we cannot assign a Kubernetes cluster per team or per service or whatever. So we had to have RBAC in order to protect the various tenants of the infrastructure from each other. We have a policy of applying one namespace per service. And the result of that is Conway's law. For those of you who do not know Conway's law, it says basically that the organizational structure, or the structure of your organization, is going to show up in your products. And what has happened in the past in our organization is that there have been a lot of changes, and we were kind of in flux in the last few years. So we decided, instead of going to a team-centric approach, to go for a product-centric approach, where product is, of course, the service. Authentication-wise, we use currently token auth file. We have evaluated all the various authentication modules. There is actually a Fabricator task in our Fabricator. It's fabricator.wikimedia.org, so go see if you want. It's written by yours truly, and it evaluates each one of those authentication methods and why we ended up with token auth, which is a little bit difficult to maintain. But we would like at some point to go to the webhook authentication mode, but we first need to run a service that actually allows you to auth against. The admission controllers that we have are the standards that are the standard admission controllers that we run for our Kubernetes version. We have not deviated from that. What we have done, however, is that we have Firm, which is a wrapper around IP6 tables and IP tables that makes managing rules via these tools way, way, way more easier. So we have this across the entire fleet. There is not a box without, well, there is not a box. That cannot be absolutely true, but anyway. So most of the boxes have Firm there, and they have default policy of drop. And that specific thing also is applied on the Kubernetes nodes and, of course, the API servers. We were kind of worried about this because we also applied firm to our OpenStack boxes. And, well, there are race conditions. You reload firm, and it flashes, of course, the entire rule set of IP tables, and then Nova Network does not notice because Nova Network just executes commands and does not monitor anything. And of course, you're left without the rules, the firewall rules, and default drop, and you're dead in the water. The good thing is that both kubeproxy and kubelet and the Felix agent, which is what Calico names the thing that runs on your node, all monitor, and now they all fix the rules, and this thing works way better than we feared. So let's go a little bit into network. This is our typical primary DC. These are 4 rack rows, as you can see, we're in one of those adding a 5th one, and every rack row is comprised of 8 racks, and every rack row has one TOR, top of the rack switch, and they are stacked into being a single managed switch, which means that basically if you reboot that specific switch, the entire rack row, which is 32 racks, is going to go down for the duration of the reboot, which, by the way, Juniper does take a little bit of time in that big switches. It's a little bit of a collapsed class topology, if you want to be not very pedantic about it, in the form that we have those QFX switches which are basically 10G port switches that are the spines, and there are all the X switches that are the leaves. The thing to note in this specific diagram is the fact that if you have a box in one rack row, in order to reach any other box in any other rack row, you have to go through the routers. Now, we might have quite a bit of traffic outbound, but in between rack rows, it's not that huge. And it's fine for us to use those routers because we feel that at this specific point in time, layer 3 is more debuggable than layer 2. A little bit more about it. So we have currently the clusters are rather small. They're 4 machines. And so we have 1 per row, but we plan to increase these to 12 very soon. And we had this requirement since the beginning that the Kubernetes clusters needed to be fully compatible with the legacy infrastructure, where legacy is what we currently have, which meant that we could not do NAT, no network under translation anywhere. We started looking at the various solutions, and 2 years ago at FOSDEM in 2016, there was a Calico talk. We looked at it and we said, whoa, this thing is what we need. What Calico does is that you have an agent in every one of your nodes, and it talks BGP with either all the other nodes or with your routers or whatever you tell it. It's fully configurable, and it announces the pod IPs to the rest of the world. So what we have done, we have it configured, again, via Puppet. Well, partly via Puppet, partly manual, because there are 2 things that we do not currently do via Puppet in Calico, and those are the IP pools and the BGP peers, the routers, basically. And it's working quite fine, and we're rather happy with it. We do not do BGP full mesh. That would be all the nodes talking to each other and exchanging the routes of the pods so that you would have one only hop for one pod to reach another, because as I said, we have this rack row aware networking diagram where you have to go via the router in order to reach a different rack row. We're thinking about row-specific full mesh, though, in order to keep it more local, have more affinity in the rack row for inter-pod traffic. We are using 10.x/8 IP addresses for the pods, and they're fully routable in our network thanks to Calico. And we are using the exact same IPs for the exact same, not the exact same IP space, but a different /24 for the service IPs. And this is the part where you'll say service IPs are not really routable in Kubernetes. They're not really IPs to start with. They are tags, basically. You say the pod just needs to have an IP to talk to. So those are effectively just reservations. We just reserved IP spaces because we do not want to have 190 to 168 IPs in our network, because whenever we met those, for some reason, it was due to either a misconfiguration or something very confusing going on. So it was just maintaining the status quo. And one thing that Calico has allowed us to do, and was very, very nice, and thank you, Calico, for that, is we now have, even though Kubernetes does not support IPv6, well, at least in our version, our pods are IPv6 enabled. And in order to do that, it was very easy to do that. In the IPAM for Calico, we just said assign IPv4 true, assign IPv6 true, and then we had to go to every node and set those to sysctl configurations that you see there. Now, for those that have ever had to do IPv4 forwarding and haven't done IPv6 forwarding on Linux, that thing does not do what it does in IPv4. Go read the docs, they are completely different. They do different things. The second one is because we wanted to have routing in IPv6 in our nodes, but at the same time, we did not have to go around and manage all the aspects of a router in Linux. And that value there, accept array equals 2, allows the nodes to receive router advertisements from our Juniper routers in order to continue working as the normal boxes that we know, plus having the capability of forwarding IPv6 packets for the pods. We also have network policies, kind of. So for those of you who don't know, 1.7 does not support Ingress. 1.8 does. So we had to work around that. We're hoping to drop that workaround in the future in 1.8. Calico does support Ingress, and that's how we implemented our workaround. And the second thing that we met was the fact that 1.7 does not allow you to change a network policy. You have to bring it down and reinstall it in order to change the policy. And we had to do that via Helm. The alternative that we have actually implemented is we patched the Calico KDS controller. The version was 0.60, and it's a Python one, and it's no longer there because it was rewritten in Go. So our solution, well, it's not needed anymore. Thankfully, with 1.8, we don't even need that. It was really, really small. We have a default Ingress policy, and our patch is like very minimal, 14 lines of code. All it does is read a config map and populate the Calico configurations. What about Ingress? We evaluated back in 2017 and said, nope, not yet, not ready, not for us. So how do we route traffic to our clusters, you'll ask? And that's a pretty valid question. So what we do is we use that Python in-house built daemon that we have been having for like, what it is now, 8 years maybe. It's called Pyball, and there's a URL for you in GitHub if you want to go and take a look. What it does is it monitors LVSDR entries in the kernel. LVSDR, LVS direct routing, what it basically does is when the packet reaches the load balancer, the only thing that it does to the IP packet is change the MAC. It doesn't alter in any way the IPv headers or anything like that. So it's very, very lightweight, and the traffic goes directly to the backend. That means, however, that the backend needs to have that IP set up in its interfaces, otherwise it's not going to accept the traffic. The good thing is that it does not have to reply back to the load balancer, and the load balancer does not have to reply to the client. Outgoing traffic leaves all the backends and goes straight back to the client instead of going through your load balancers, which is good in our case because we have minimal input traffic. It's basically get slash and article, but we have a lot of outgoing traffic from those boxes. We had a lot of expertise over this software, and we decided to reuse it. And we know from a blog post from GitHub that they have more or less a similar approach, a little bit different, but we're happy with at least we're not alone in this. And we're using node port in order to, with external IPs. That changed, by the way, in Kubernetes 1.6, if I remember correctly. It used to be different in the API. That caught us off surprise for a little bit, then figured out that this is actually a better way. About metrics collection, we actually connect metrics. Thank you, Prometheus, for that. It works quite well. And the only thing that we did was have Puppet populate the configuration. So what we do have is that Prometheus discovers the API and polls the kubelets the advisor. It also polls the kubelet API itself, and we've met a bug in 1.73 where the API is was a little bit different. The interesting thing with that was that the Prometheus community already documented this in the example configuration. That was great. However, applications are a little bit more interesting. So we also use Prometheus for that too. What we did is all of our applications historically use statsd. So we have a statsd exporter. That's a sidecar container to all of our pods. Applications talk to localhost and push all the statsd metrics. And then Prometheus discovers all the pods and polls all the pods and gathers the information. And we visualize all of that through Grafana. And here's a link if you want to get our Grafana installation. A big kudos to the Grafana team. This is an excellent software. Thank you very much for that. I'm pretty sure you all know it. It's just a shout out. Alerting is not that great currently, and this is mostly for hysterical reasons. We use Prometheus again, but partly because we're still an Isinga shop. Isinga, for those of you who do not know, it's an old software from the 90s. It's very node-centric, not service-centric. We want to migrate off of it. We have started by integrating check Prometheus metric script in Bash, and of course we had problems with it because it did not support floats, and various other small corner cases, and then we ended up rewriting it in Python. And if you add in Puppet, which is how we manage all of our alerts, you can get that very, very weird-looking alert, like what does this thing even do? We're fixing this. One of my colleagues actually, while we were here, submitted patches to fix this, and all of the alerts themselves are now in the Prometheus engine, and we just pulled a very specific named alert for that. The last thing that we did is that we decided to go forward with a different way of monitoring applications than what Isinga did, because basically HTTP applications are a little bit difficult to monitor when it comes to APIs, because each of one of the endpoints can fail in a myriad ways, and all of the other points may not fail. So it's difficult to go around and create a software that monitors all of these APIs and have it Isinga compatible and all that. So what we did is we extended our Swagger specs for all these applications with a very specific spec that allowed us to create a checker that would go around, walk all the API and the endpoints, and submit a test query to that specific endpoint. And that's where I pass the ball again to Giuseppe.
Okay, so so we called the project Streamlined Service Delivery because the main point for us was that Kubernetes allows you to change the way you manage this life cycle of software, and specifically a microservice, from development to production. There is this big schema of what we did, which is pretty detailed. I won't get into that, or I'll let you leave at 6 o'clock. I'm just going to concentrate on the details of deploy stage. If you want to see the details of everything, where it's all documented on Wiki, so if you just search with enough tenacity, you will find all the documentation about this. Let's just concentrate on deployments. So as we said, we have one namespace per service, basically. And we will have several people that should be allowed to deploy to that service, but we want people to be abstracted from the problem of knowing the details of how Kubernetes works. So we use Helm, which is working very well for us. How did we set up Helm in production so that we could secure the installation as much as possible? What we did is that we have one tiller instance running in each namespace with specific airbag rules, which are basically what is suggested in the guide from Tiller, apart from the fact that we also need to set up networking rules for Ingress, because we basically whitelist the ability of a pod to call other pods to make connections to other pods. And then we have a deploy user, which is just allowed by airbag to speak with Tiller, basically. So the only thing that somebody that has the credentials for the deploy users can do is use Helm, basically, on the cluster. They can't use kubectl. So we restricted the use of kubectl to administrators, and normal deployers just have to use Helm. They don't have to care about the intricacies. They can basically shoot themselves in the foot with kubectl. All of this is implemented with a very simple and kind of shameful at the moment wrapper around Helm. This wrapper does some more things. We said we have two primary data centers. Most things that we deploy, all things that we deploy on Kubernetes at the moment are active between the two data centers. So we want release to go to both data centers, and this wrapper does that. And also we are working at the moment, we hope to be finished before the conference, but we're not, on doing canary releases. The way we do it is pretty simple. We cheat. Basically, we have two Helm releases for each practical release, a canary release with a small set of replicas, and then a production release that has a larger set of replicas and the service definition that has selectors to select all the pods from both releases. Whenever we do a new release, we first do the Helm first upgrades the canary release. We check the metrics and the logs to see if everything's green. We go on and deploy to the production part. So basically what we do is proper canarying, the number of people that are proportional to the amount of replicas in the two clusters. We get the new version for a small amount of time. And if we don't roll back after a few minutes, everybody's getting the new version. Finally, as I said, it's a shameful bash script at the moment. What we plan to do is to try to rewrite everything, including this part, as Helm plugins, so that we can basically share this with the rest of the community. Finally, we have our very own and very new Helm repo, which at the moment has just one chart, which is a public repo, so that anybody can run the services that we run in production using our Helm charts in the future, and there's the link. And finally, since we're almost done, and I think everybody's very tired at this point of the conference, I want to thank you for sticking with us until 5 o'clock. And a shameful plug, as I said, our team is too small and we're hiring at the moment. And I'm leaving this slide because you have some links to the resources that you can consult. Remember, we're a 100% free software shop, so everything we've talked about and everything we do is publicly available as free software, and you can take a look and even contribute if you want to. So that concludes our talk. We have a couple of minutes available, and if somebody has questions, we are here to answer them.
Over there.
What's the question? Sorry.
The slide said you're thinking about rocket.
Sorry, I can't hear you. Take a microphone. Sorry.
No problem. The slide said you were thinking about moving from Docker to Rocket. What's motivating that mindset?
The question is about why we evaluated Rocket. I think Rocket has some interesting characteristics, the most interesting of which, from our perspective, is the ability to use the TPM to verify the images and to check consistency. We're very concerned with security. Remember, our site is a site that accepts arbitrary input both in text and binary form, because Wikimedia Commons accept binary forms as well. So we have to be very, very careful with security. And that was one thing that seemed appealing. I don't think that the support for Rocket was there when we decided to deploy Kubernetes in production into Kubernetes, so we're sticking with Docker for now. And we have quite some tooling around Docker. We would have to adapt that to Rocket whenever we want to do that.
Giuseppe? Yeah.
Sorry?
You called the session installing on bare metal. So you're installing the Kubernetes or all your Dockers on bare metal or on virtual machines?
The virtual machines are only the API servers. Everything else is bare metal.
The server is being
Dedicated as Kubernetes.
namespaces and pods.
Mm-hmm.
Yes. Yes. So the physical servers are used for running pods and all the applications, basically. Okay, I don't think if there are any other questions, and don't see anybody because I'm blinded by the lights, but if you have questions, we are just around for a few more minutes. Thank you again.